let's continue further into the fundamental field of calculus. So now with the consequence that we have had from the fundamental field of calculus, and we've done a couple of the net change, net area, and area problem that in the earlier lectures. Now let's even put that even a little further. So we're going to apply our understanding into the thinking some more about the symmetry of the function. So that make it sounds like it's some topic right here, but really it's what I'm pointing out, what I'm about to teach here is simply an option of how you handle your work, how you calculate your integral work. And so first of all, you guys still remember from your pre-calculus courses, there's the concept about functions being odd and being even. Yes. Okay. So a function, as a definition for a function being odd, right here means the function value at minus x has to equal the negative of fx. So that's the algebraic definition of that. That's really the deal with here. But basically, what it means is when you're putting up the graph, right? The graph has the function has the symmetry through the origin, right? So every point here on one side of the graph has an exact mirror reflection through the origin. Okay? That's called the odd symmetry. Okay? And then a function being even means if you're substituting a negative input. See, we're starting out testing by substituting a negative input. And if it turns out to be exactly the same as the function at the positive input, okay, then that's an even function. And so example could be something like this. When you're putting it in the graph, see, when you put it in the graph, the left-hand side, any point on one side, right, has an exact mirror image on the left-hand side through the y-axis. So anytime your function is having even symmetry, it's reflexive, right, through that, it's symmetric through that y-axis. Whereas in the odd symmetry, it's symmetric through the origin. Okay? So that's some brief reminder of that. So now, but then in the end, being symmetry is always around, it's all about being around the center here, right? Either the center being the origin, but right on the y-axis right here. And then again, being the center right on the y-axis. And so think about that impact here. When we take this understanding into our function, into our the function with the integral here, in our understanding of the integral. Think about it, an interval like this. Right? On it doesn't matter about the graph, but on any interval, we always, a lot of times when you're working with those intervals, I call the symmetric intervals. It's starting from minus a to a positive a, like a minus 3 to 3 or minus 4 to 4. Those symmetric intervals on the x-axis, right? So if your function is odd like this, inside of that interval, then the integral from minus a to a. So think about this f of x here, right? Is odd symmetry. It's going to have some shape like that, right? So one side is going negative, one side is going positive. So the integral like that, think about it. The accumulation goes all the way from minus a to a, but some accumulation total up being negative, and some other accumulation goes total up into a positive quantity. See what I'm saying there? So in the end, what do you think the final integral value has to be? Zero. See what I'm saying there? So we took advantage of, hey, if we know, so knowing this, if you can take advantage of that, it will speed up your work a lot of time. See what I'm saying there? So as a quick example over here, and I'm not saying that it's a must that you always have to go with this, but it's all about this kind of problem right here. It's just about an option when you handle your work. So as an example, right, then when you're asked to evaluate, right, when you're asked to evaluate the integral from minus 4 to 4, but your function here is x cubed minus x cubed minus x. Right? The x. Okay. So I don't even see the graph for this, but think about this function right here, and this is just brain work here, right? The brain processing work here. The number one thing, the interval here is a symmetric interval, right? It runs from a negative 4 to 4. See what I'm saying there? And the function itself, think about this function, x cubed minus x here. Right? This function here, I can tell you, is odd here. Right? So how do I know that? Well, I can quickly substitute in like a minus x here. Right? Minus x, substituting into the function that gives me a minus x all cubed minus x. So I'm talking about we purposely substituting a negative number, a negative input. And then look at what it turns out right here. It will turn out to be, so minus x all cubed becomes minus x cubed, right? And then the minus with the minus becomes plus x. We look at that. Okay. And so in that way, this is the exact opposite of our function. Right? Because you can factor out that minus sign, making it x cubed minus x. That's, I observe it's the exact opposite. That's one way of arguing it using the algebra. When it comes to this, it's just about the mind process, so you don't always have to do this. Think about the powers here. It's a polynomial. The x cubed minus 3, x cubed minus x right here. This is power 1, right? Your function in the end, your fx here is a polynomial. It's a polynomial. Okay? So being a polynomial, see? This combination of the powers here, odd powers and odd powers, if the combination is all odd powers here, your function is odd. See what I'm saying? So polynomial with all odd powers, right? That leads to your function here is odd. But I'm talking about this trick right here is only applicable to polynomials, right? Don't use that for the e to the x, and don't use that for the sine of x or whatever. Each one. Those functions are outside of the polynomial family. Okay? But so now that's just a different way of recognizing your function being odd. So now being odd, right? What's good about that? So the integral, yes, even though you can do the formal work, but the integral can just easily be coming out as a 0 over here. See what I'm saying? Simply our reasoning because f of x is odd. So I gave the explanation and all that, and why we recognize it, how we recognize it as odd, right? See, and if you really want to spend your time doing the integral, that's fine, right? The antiderivative for that goes 1/4 x to the 4th, right? Minus 1/2 x squared, right? And then we're evaluating from the minus 4 to 4, right? Go ahead and quickly substitute it and verify it again. See if we get a 0. So, back to the other board. Yeah. You should be able to confirm that that was all 0. So now what if your function is known to be even? Okay. That was one case when your function is odd. Now again for an interval, okay, from minus a to a, right, and what if your function is an even function? Okay, having a shape like that. Then even symmetry. Just once again, it's just something that if we can recognize, right, then we gonna be able to apply this understanding right here. Think about the accumulation, the integral from minus a to a of the function f of x dx. So that goes like this, right? Goes like that. It's all positive. Then it also goes like that. The exact symmetry over. So it's not going to be 0 for sure, right? It's not going to be 0 for sure, but it's going to be what? You can see that you can just simply do one side from 0 out to one side again. See what I'm saying? And then double that. So the integral from 0 to a over here, and double that. That's one way. Or you can think of that as the integral from minus a to 0 to one side, right? And double that. That would work. Once again, it's just another option that we can start putting in use again at any time that we recognize our function is either being having odd or even symmetry. Okay. And then we can quickly apply that in an example like this. I keep bringing up the polynomial because for polynomials, a lot of times it's easy for us to recognize the symmetry of the polynomial. Right? By just picking up. I've been looking at the combination of those powers. So it's a power 4, right? Constant is a power 0. See what I'm saying? No? So in the end, this polynomial over here, x to the 4th minus 1, right, is even. Right? Or for sure, we know it's going to be even the symmetry. So, and we don't even need the graph for that, right? We just look at the nature of the function right here, right? Because of the even powers, right? Yeah. But remember, this reasoning is only applicable to the word of polynomial. You know what I'm saying, no? So your integral can be speed up a little bit. I mean, it's not necessarily a lot faster, not really, but we can do this. It's going to be a 0 from 0 to 3 like that, right? We chop that into only half of the interval. And then we go x to the 4th minus 1, right, dx. Right? So that's making it the next step right here, 1 to the 5th, x to the 5th, minus x, right? And then 0 to the 3. But the part that speeding it up a little bit is that we can save ourselves from substituting in the 0. The 0 substituting in is all going to 0 out. See what I mean? Right, so we only in the end have to worry about substituting 3 into the function. So I'm looking at a 1/5 times 3 to the 5th, right? Minus 3 to the 5th. Okay. So it's going to be 243, if I do my math correctly, over 5 minus 3, and whatever else comes after that. You're right. My bad. Thank you for reminding me that. Yes. Multiply that by 2. Should have done that. Okay. All of these answers here need to be multiplied by 2. 2.1, 2.3 over 5, right? Minus 3, whatever that is. Multiply by 2. Yes. Got that.